Welcome to this lecture on the equations of line in the Cartesian plane. So in this lecture, what I'm going to demonstrate is how you can represent a line on the Cartesian coordinate two-dimensional plane. The relevance of a line, the equations of a line on the Cartesian plane is that the line is one of the most commonly used concepts in all branches of mathematics. It has higher order applications in wherever math related subjects are involved, such as economics, the sciences, statistics, and where not. So it's absolutely essential that anybody who is engaging in using mathematics for econometric or any kind of mathematical analysis is aware of these equations. So first I'll take you through the base equations, and then we will I will run this in a dynamic way with using a real-time equation system. So having said that, let's get started. So the most common way of interpreting a line it's called the slope-intercept form, and that goes something like this: y equals mx plus c, where m is called the slope of a line and c is called the intercept. Now this is on the y-axis. Now don't worry if this comes across as a bit abstract now, because once we run this on the tutorial, it will hopefully become much clearer to you. Now the second form of representing a line, that is called the 2-point form, so which means that you have 2 points, x1 and x2. Now suppose we represent this as p, this is q, x1 comma y1 is 1 point, the second one is x2 comma y2, and the way you would graph this a line here would be y minus y1 divided by x minus x1 equals y2 minus y1 divided by x2 minus x1. Y minus y1 by x minus x1 equals y2 minus y1 by x2 minus y1. So what it says is that if you know 2 points, then that uniquely defines a line. So the first one, we said this is a slope-intercept form. This is a 2-point form. The third one that we have, this is called the 2-intercept form, which goes something like this: x by a plus y by b will be equal to 1, where so this is the coordinate plane. Basically says that these are the 2 intercepts that you have. This would be a comma 0, and this would be y-intercept 0 comma b. Now you would note that what this essentially says is that if you know the slope m and the y-intercept c, then it says that this uniquely defines a line. Similarly here, if you have the point p1 and the point p2, that uniquely defines a line. Similarly here, you have these two that uniquely defines a line. Now this is a theory. As I said, at this point, if you're not familiar at all with the equation of a line, you've never heard of that before, this will certainly come across as very abstract. But what we'll do now is it will really demonstrate to you why this is so valuable. So let's first start with we'll start with the slope-intercept form here. So this is what we said. You have the this is the line in the 2-intercept form. We will use a slope-intercept. Yeah, this is the one that you have. So the slope-intercept form, y equal to mx plus b. So here I said m equal to b. We can define m and b here See, this equation system is, this is a Cartesian coordinate plane that you have. This is the x-axis and this is the y-axis. And if you define m and you define m, so in this case I have set, just input the equations, y equal to mx plus b at m equal to 1 and b equal to 1. This is really what you're seeing. So the intercept here is, this is line 0 comma 1 and this is m. And I'm going to simulate this on a plane where m is set up from minus 10 to 10 and b from minus 10 to 10. So you can see how this really, you just make this a little slower. Yeah, you can see that it just slows down. You can really see how the workings here. Look at this. See, watch this. When m becomes, it goes from as m decreases here, you see that the slope increases in the negative direction. So we'll just pause B for a moment. We'll just focus on m. Just watch this. When the slope decreases, you can see that m goes from minus 5, it goes to minus 4. So you can see that how that the slope of that line is changing here. Look at this. So at this point, for example, we take a snapshot. M equal to 1.9, and we have said B is 1.9 as well, and at this slope, which is you can see how this pans out here. So now just run B for this given slope. Watch this. And at the point where this is 7 point and is roughly about 8, you see that let us pull down this graph. Yeah, this is exactly at 8. So this is the y-intercept for you. Trying back into our equation. So this is the y-intercept I said. And then this is a slope m. So that's exactly what you're seeing. Slope is at minus 1.9. So let's say, suppose that I move the slope to exactly to 1. Just so that you can demonstrate. Yeah, look at this. This is the case where the slope is 45 degrees, so tan 45 is 1. That's what you're seeing here. And on the slope on the intercept B, this is what you get. Okay, I hope this is clear to you now. Now let's look at the 2-point form. Same thing. What I've done here is I've set up 2 points, x1, y1 and x2, y2, and I have labeled this so that this is absolutely clear to you. And we are running x1 from 0 to 100 and from y1 from 0 to 100. Then again we have x2 which we are running from minus 100 to 0, y2 from minus 100 to 0, and then we'll just so let's just look at this at the current point. You have in this case 5 comma 60 is your first point and minus 8 comma minus 7 is your second point. And you look at this, how this line is absolutely defined by these 2 points here. And then let's just run this dynamically and see, the benefit of running this is that, running a simulation, which we are able to do this because of, the excellent developments in computation. In fact, before all this, mathematicians used to graph this out manually. But benefit is, and you can see how when this line moves, how this line keeps on changing. So absolutely that the dynamics of of the points and the relation to forming the line, that becomes very clear. So there you have it. That is your that is a 2-point form. Now we'll also see the intercept form. Now this graph is, this form of the equation it's less common, but it's nevertheless it's quite useful, because you can look at so let's set a2 minus 2 0 and b2 0 1 here, and then just look at this is your y-intercept and this is your x-intercept. So minus 2 comma 0 and the 0 comma 1. So in fact, what we can also do is I'll just label this out so that it's clear to you. Um, so we just what one point will be a comma 0. Then we close the parenthesis, and then you have 0 comma b, and we just label this. Yeah. And then we can see that we are minus 2 0 and 0 comma 1. Just run this here. Okay. So this it helps you to see how really this again the two intercepts, they completely define the line. So I would encourage that you try this, you graph it out for different values of m and c, and then again for the for various different point groups, again for the intercepts as well. Now the key takeaway I would say from aside from from these equations is that for a line on I'm stressing that this is on the two-dimensional plane. On the two-dimensional plane, you have a line. For a line will always be it will be linear. Both both across x and y it will be linear, and and using these three systems. In fact, these three systems are you could say these are equivalent forms. If you look at this carefully, you'll see that yourself. For example, the slope m is nothing but you take my y2 minus y1 divided by x2 minus x1. That's nothing but that's really your slope. Or the these are, you can, using algebra, you can actually derive the from any one form you can derive the others as well. Okay, thank you.